Okay, so it's great pleasure to have Natalia Castellana today in the topology seminar. So she's from Universitat Autónoma de Barcelona, and we are going to hear about the normalizer decomposition of p-local compact groups. So Natalia,
Okay.
please take it away.
Okay, thank you. Can you see the screen?
Yes, screen is visible.
Okay, so, well, first, I prepared a talk for a very general audience. Now I'm not sure that I did it right, but you can stop and ask. And so this project I'm going to talk about grew up out of women in topology, one of these women in topology projects. And my co-authors are Eva Belmont, Jelena Grbic, Kathryn Lesh, and Strumila. So our backgrounds were very different from each other. So the point was to find a project that we could start together from the very beginning. So we started with very basics in the theory. So let me show where the normalizer decomposition fits, and then I will talk about the notion of a p-local compact group. So the idea is the following. So we have a compact Lie group. Can you see if I move my cursor around the screen?
Yes,
oh,
the cursor is
yeah,
visible.
yeah, because this is not the usual device I use for talks, so it's more minimal than the one I use. So we start with a compact Lie group. Every compact Lie group admits a maximal torus, which is a torus which is maximal in the sense of inclusions and conjugacy. Any other torus is subconjugated to this maximal torus, is a maximal connected abelian subgroup of G. NGT is the normalizer of this maximal torus inside G, and the bile group is the quotient of NGT mod T. Yeah, T is a normal subgroup in the normalizer, and then you take the quotient. This is the bile group, and the bile group is a finite group with a lot of structure, which is very well known and studied. But the fact that I want to point out is that the inclusion of the normalizer of the maximal torus of G inside G induces a map on classifying spaces, which is a mod P equivalence if P does not divide the order of the bile group, which is a finite group. So this was known. It builds out of the transfer for vibrations in this context. So in a paper in the proceedings of Arcata written by Jakowski and so this is wrong. It's Jakowski McClure. It's not Jakowski Oliver. Now I realize Jakowski McClure. They ask what happens if P divides the order of this bile group. And a first answer to this question appears in the work of Dwyer, Miller, and Wilkerson, where they describe two classifying spaces, the ones of SU2 at SU3 at the prime 2, by using a pushout. And the pushouts are the following one. You have on one corner, you have the normalizer of the maximal torus. And inside this normalizer of the maximal torus, there is a quaternion group of order 16. And this also sits inside of a binary octahedral group. Yeah. And these groups, they sit inside SU2. They use representations of these groups, and they all sit inside SU2. And this push out they show is a mod 2 equivalent with BSU2. It says that at the prime 2, BSU2 can be described as a push out of proper subgroups. One particularity of these subgroups is that, for example, NGT is a p-toral group, is an extension of a torus by a 2 group, because the bile group of SU2 is Z mod 2. So this NGT is just an extension of a torus by Z mod 2. And the other groups are 2 groups, right? And well, SO3 is a central quotient of SU2, and then there's a similar decomposition. In that case, you also again have the normalizer of the maximal torus in SO3. Again, you have a torus and Z mod 2 acting. The difference is one of the extensions is a split and the other is not. Q8 is the quaternion group. And then you have an octahedral group, which is sigma 4. And taking this pushout, they also show that this pushout is mod 2 equivalent to BSO3. And again, I want to point out this, that you have 2 groups, and NGT, which is an extension of a torus by a 2 group, right? So this one consider this as a first positive answer to the question is of what happens if P divides the order of the bile group. Right? But in this paper, in the proceeding, Jakowski and McClure reinterpret these pushouts in the context of the orbit category and collections of subgroups. Right? They consider inside, for example, for SU2, you can consider the quaternion group Q8. And then it turns out that this binary octahedral group is just the normalizer of this quaternion group in G. And the intersection of this normalizer and NGT is just this Q16, right? This quaternion group. So this diagram, I want to say that the proof in Dwyer, Miller, and Wilkerson to show that these pushouts is a mod P equivalence, they use a strongly geometry, and what they show, in fact, is that all the homotopy fibers sitting over SU2, they give you pushout, which is mod 2 acyclic, but they use the geometry of the action of G. And here they reinterpret this in terms of the orbit category. By the orbit category, I mean the orbit in which the objects are orbits, G mod H, where H, if you fix a collection of subgroups, H is an element in this collection of subgroups. And the morphisms are the G equivalent maps between orbits, right? G equivalent between these G orbits. So they consider these orbit categories, and the family, the collection of groups they consider are just made by the quaternion group and the torus on one side. And for SO3, they have a similar description in which this the quaternion group turns out to be the intersection of the normalizer of an elementary abelian group, Z2 and Z2, just diagonal matrices in SO3, and intersection with NGT, right? And the group is the octahedral group is just NGB, the normalizer of this element. So give another point of view of those groups which appear in this pushout. If you only consider the orbit category of these 2 pairs of groups, and in this small diagram on the right, just you have the maximal torus, and inside the maximal torus you consider this quaternion group on one hand, or you consider this elementary abelian 2 subgroup for SO3, and they fit in a small subcategory of the orbit category, in which you have automorphisms on one side, automorphisms on the other, and only arrows on one direction. So the way that Jakowski and McClure reinterpret these pushouts in terms of the orbit categories, just they show that if you consider a motopico limit over a category of this shape, that in that case that could be, if you take the orbit category, the functor would be taking the Borel construction on the orbits. You can reinterpret a motopico limit on a category of this shape as a homotopy pushout. There is a way of describing homotopico limits over this category as pushouts, in which you have to just find which groups you need to put in each corner of the pushout. So they give this point of view of these pushouts as being equivalent in some sense to some colimits over an orbit category. And at the same time, they introduce the terms of being a collection being p-dense, which is p-dense essentially means that you can recover the homotopy type of BG out of these small collections. And in fact, they describe a new example apart from these Dwyer-Miller-Wilkerson examples as a pushout, which is SU3. They describe also SU3, and they consider the maximal torus, and they consider also some diagonal in the maximal torus. But they give another example to show this pattern, that you have this a small orbit category that you can rewrite as a pushout. Yeah.
Natalia, can I ask a question?
Yeah.
This is very naive, bad question probably, but if you have maps in the orbit category, that usually exists when you have the subgroup on the orbit stabilizers on the left is a conjugate to the stabilizers on the right, like H should be a subgroup of K up to conjugation.
Yeah. Yeah.
So in that sense, how do you put the Q inside the torus? Q8 quaternion group?
Oh no, that's B and Q.
So on the left side, you have the Q and maps into T. How do you define that?
This is the quaternion group in SU2, right?
Okay, and T in this case is still the torus.
Q16. Now I have to think about it.
So you put inside the extension of T, is that NGT?
T NGT, right? Sorry, now I didn't follow your.
So you are mapping Q inside not T, but NGT.
Oh, NGT. Sorry, I think T is N. Yeah, T must be NGT. Sorry. Yeah, in the small diagram below. In the small diagram below, T should be NGT. Sorry.
Okay.
Yeah, you are right. Yeah. Sorry. No, what happens is the normalizer of this NGT is again NGT, and then when you take normalizer, you get the same subgroup again. Yeah, but here you have to take NGT. You are right.
Thanks.
Yeah. I just mixed because this is kind of self-normalizing, and then when you take the normalizer again appears the same group. But yeah, that should be NGT. Yeah, sorry. Yeah. Then, well, this was the first picture, and yeah, exactly. But then there was a more systematic approach to all those situations in which you can get back the mod P homotopy type of the classifying space of a compact Lie group by gluing together classifying spaces of subgroups, right? And that was the notion of an homology decomposition that appeared and were basically formalized and had a systematic approach by the work of Dwyer. But this work was based on all the previous work by Jakowski, McClure, Oliver, Benson, several people. So what we understand by homology decomposition. So the way that Dwyer made a systematic approach was by considering, I will focus now on a finite group, but his first paper dealt with, but then all this was generalized to compact Lie groups. So you have a finite group, and then homology decomposition consists of a small category, a functor, and a natural transformation from this functor to the constant functor with value 1 point on on the category which has one object and G as a let me start again. So this is a natural transformation between this functor and the constant functor Vg, which then you can project to Vg, right? So this is the data that builds a homology decomposition. You have this small category, a functor, and this natural transformation, which allows you to construct a map from this homotopy colimit into Vg. And then this is homology decomposition at a prime P if this is a mod P equivalence. Right? So the previous examples in which this theory was built off was the work of Jackowski and McClure on what was called the centralizer decomposition, and Jackowski, McClure, and Oliver in the subgroup decomposition. So each decomposition that the name centralizer of subgroup gives you a hint on which type of subgroups you will be dealing with. So for the centralizer decomposition, so the orbit category consists of, you fix some collection, and then the orbit category have the objects are elements in this family, and morphisms are group homomorphisms which are induced by conjugation in G. For the subgroup decomposition, the orbit category already appeared, so you have orbits, G mod H, where this H, the isotropy of this orbit is in this collection, and morphisms are given by G equivariant maps between these two orbits. And these were two previous decomposition known, but what Dwyer does is does a systematic study of these two decompositions at the same time and introduces what's called the transporter category. So in this case, in this category, you have objects are all subgroups in these collections, and morphisms are given by elements of the group G which subconjugate H1 into H2. So these are the morphisms are given by group elements which subconjugate H1 into H2. And then you can see that the category that describes the centralizer decomposition, it's a quotient of this category because you just take the group homomorphisms induced by those elements G, right? And on the other hand, also the orbit category can be seen as a quotient of this transporter category because when you look at G equivariant maps, you mod out by, you look at kind of representations of these group homomorphisms induced, right? Or you can just take the elements are elements of N, G, H1, H2, and you have to mod by elements of H2. It's a quotient of this. And he introduces this transporter category, and this category makes a connection between these two decompositions and other decompositions, and that's where the normalizer decomposition will show up. So there is, I try to make a picture to summarize all the information. So we have this, the nerve of this transporter category relates to both the centralizer and the subgroup decompositions, and at the same time can be described as the Borel construction on the nerve of the poset of subgroups of G, which sits in which belong to the which belong to C, right? So C is this collection we have fixed. You can look at the poset of subgroups of C as a category, and then you take the nerve of this category, and there is an action of G by conjugation. And then this transporter category, this nerve, kind of models the Borel construction of G on this poset. So we have all these maps, and what Dwyer in fact shows is that this transporter category, this nerve, is equivalent to both the objects on the left and the object on the right. Yeah, right? And there are commutative triangles which all map down to VG. So he defined what's an ample collection. It says an ample collection if these natural transformations that you have to VG are mod P equivalences. But looking at this diagram, if one is a mod P equivalence, then the other are also mod P equivalents. So that the notion of ample collection does not depend on which homology decomposition you are looking at. So if it's an ample collection, it will work both for the centralizer and the subgroup decomposition, right? And but then there is this object on the top, this poset with Borel construction of reaction of G on this poset by conjugation. So this this object can also be decomposed. And then here, remember that I told you that there was this small orbit category that could be rewrite as a pushout. So there are more general techniques to do this, and that builds to the work of Jolanta Slominska. And these are the techniques somehow that Jakowski and McClure used. She has several papers on the homotopy type of the nerve of EI categories, and he describes several techniques which are pretty general in these cases, but apply to this particular situation. He describes you can take kind of the simplices of cases, like looking at the barycentric subdivision of this poset. You take all the simplices of KC, and you construct a category, which is the category of orbit simplices for the action of G on the simplices of this poset. So you have the simplices are chains of proper subgroups in this family, and there is an action. A chain can be conjugated to another chain, and then you look at the orbits for this action. So these are the objects in this category. And the morphism, so you have a morphism from one chain to another if the target can be subconjugated to a subchain of, can be subconjugated and become a subchain of the source, right? So it's somehow describing a subdivision of this poset and the action on this subdivision, right? And then so it's possible to describe this Borel construction and this poset as a colimit over this category of orbit simplices of a functor, and this functor takes the values of this functor are the intersection of the normalizers of the elements in this family. So, and here that reminds us the pushouts that Dwyer, Miller, and Wilkerson described originally, right? So this is what is called a normalizer decomposition for a finite group, right? And this, in the sense that both the centralizer and the subgroup decompositions, they appear independently. I mean, modeling different contexts. The normalizer decomposition is introduced essentially in this work by Dwyer, trying to make this systematic approach and realizing that all these colimits are linked to a central object, which is this transporter category of G for this family, right? So in some sense, this top space here is what in some sense, it's the normalizer decomposition. Using a Slominska techniques, you can rewrite it as this homotopy colimit, right? Okay, so that's for the homology decomposition. There is all this picture. What about for compact Lie groups? Well, in fact, the centralizer and the subgroup decompositions were also known for compact Lie groups. And in the case of Jakowski and McClure, they described the centralizer decomposition for a compact Lie group for the family of elementary abelian P subgroups. And Jakowski, McClure, and Oliver describe the subgroup decompositions in the case of compact Lie groups. But in that case, instead of P subgroups, what the family would plays the role of P subgroups are the p-toral subgroups. So, and just to remind what's a p-toral subgroup of G, it's an extension of a torus by a finite P group. And the families they consider in that case are the family of what they call p-toral subgroups. That means that the normalizer of P in G mod P is finite, and this finite group has no normal P subgroup. And for this family, they work out the subgroup decomposition that then it was very successfully used to describe the automorphisms of BG, and there are a lot of describing maps between classifying spaces. But at this point, there was no normalizer decomposition for compact Lie groups. And this systematic approach for compact Lie groups was carried out by Asaf Lindman in a paper. I wrote the title of the paper because it doesn't give you a hint that it's there, but it's this orbital spaces and Quillen's theorem A.M. Minami's formula, Asaf Lindman. And he described this systematic approach, and he also shows that there is a normalizer decomposition for families of p-toral subgroups and subgroups. And it has the same property. All three decompositions, they give you a notion of ample families, because if one of them gives you a mod P isomorphism, then the other two also does. So this is kind of a general framework for decompositions, right? So the normal decomposition has sometimes a different flavor from the other two, but it has advantages. Yeah. Now let's move to the second part of the title, p-local compact groups. So p-local compact groups, essentially, we are going to talk about what's called the fusion systems on discrete p-toral groups, right? So let me give you a motivation for this framework. So we have been talking about how to decompose or reconstruct BG, the classifying space of BG, from classifying spaces of subgroups at a prime. But if you are only looking at the cohomology and you ask whether the cohomology of G is determined by the cohomology of certain subgroups, this was already known much before, and it's essentially what the stable elements formula tells you. Right? So the stable elements formula, which goes back to the work of Cartan and Ellenberg, and builds out of the transfer and the properties of the transfer, the double coset formula. It tells you that the cohomology of G, well, I've written it in a kind of a modern form. So for Cartan and Ellenberg will say that the cohomology of G injects into the cohomology of a Sylow subgroup, and the image of this Sylow subgroup and the image of the cohomology inside the cohomology of the Sylow subgroup can be described as elements which are stable under what I wrote here, the inclusions and conjugacy relations inside G, right? And that corresponds to the limit of the cohomology of the P subgroups with respect to inclusions and conjugacy relations. Right? So if we could think of this as also in the same flavor as homology decompositions, here we just we describe the cohomology of G in terms of the cohomology of subgroups and some relations, right? So if you want to know if, I mean, sometimes I think of it as this is giving you a system of equations to solve for when an element belongs to the cohomology of G, when you are inside the cohomology of the Sylow subgroups, right? So so in some sense, you can think that this is kind of a shadow of the homology decompositions. There are spectral sequences for computing the cohomology of a homotopic limit, which relate the higher limits of the cohomology of the pieces to the cohomology of the colimit. So this is kind of what could saying this is like one column in one of these terms in the spectral sequence. So so now let's focus on the indexing category. So in the indexing category, what you have all p subgroups, and you encode all these p subgroups in a way that you want to keep track of the inclusions and the conjugacy relations. And you can do that in a category, right? So you can consider a category of a category in which you can fix, well, you can take all subgroups of G, all p subgroups of G, and morphisms induced by just group morphisms induced by conjugacy. And this is the category that already appeared in the centralizer decomposition. So if you only look at this indexing category, what Puch introduces the notion of a saturated fusion system. And the idea is that, well, if you look at the cohomology of G, it seems that only the p subgroups of G and how they relate by conjugacy is relevant to describe the cohomology of G. So let's try to just encode this in the category, and just to try to isolate which are the properties of this category which are really relevant to describe the cohomology of G. And then this is what it's a fusion system that was introduced by Louis Puch. And for a finite group, so it goes to, I will not write all the axioms, but so if S is a finite P group, a fusion system is a subcategory of the category of groups. That means that all group, the morphisms in this category are group homomorphisms. Objects are all P subgroups inside S, and these morphisms contain only monomorphisms, and they must contain all those which are induced by conjugation in S. These are, they have to be in the category. And condition B, it says that every morphism factors as a composite of an iso and a subgroup inclusion. So the subgroup inclusions are already in the category because are induced by an element, but it's a conjugation by the trivial element S, but you ask also that this iso has to belong to the category F. And then there are some saturation axioms which I won't describe because they will not be relevant for what I'm going to say, but those are the ones which make this abstract categories just to behave really like the categories which are induced from a group, even you don't have a group in the picture. So that the main example is if you have a silo P subgroup, you can consider what's called the fusion category of G with respect to S. And it's just the group homomorphisms are just, the morphisms in the category are the group homomorphisms induced by conjugation in G. Right? And the point what make all this theory interesting is that there are also exotic examples which can be proven not to be of the type FSG for any G. And there are several examples like Benson, Brotolevin, Oliver with Viruel. So there are a lot of examples in this theory which do not correspond to FSG. Okay, so that's the case for finite groups. But that's also, this is only moving this is what Louis Puch introduced, the notion of a saturated fusion system. And then what Brotolevin and Oliver did was to study the homotopy theory of these fusion systems. And what do I mean by the homotopy theory of these fusion systems? Well, once you are given a saturated fusion system, let's say F, you can construct a stable element. So let me go back. So if you look at this formula, so you can replace the indexing category by a fusion system, and it makes sense to consider this limit. You can consider the limit of this fusion system of the cohomology of the p subgroups that you have in your saturated fusion system. So, and that gives you an algebra. And then you can ask whether this algebra is the cohomology of anything. So the right-hand side makes sense for any abstract fusion system, but it's not clear is that the left-hand side has any sense, because that could not happen, that this is not the cohomology of anything, right? So what Brotolevy and Oliver somehow, well, this is kind of my point of view, they answer these questions, because if there is such an X, such that realizes these stable elements with respect to a fusion system, this X has all the right to be called a classifying space of something. So it should be the classifying space of the fusion system, right? And so Brotolevy and Oliver started answering this question in their paper on the homotopy type of fusion systems. So they introduce a new category, which is the centric linking system, with some properties, with some axioms associated, that could be associated to a fusion system. And they show that the cohomology of this linking system, the p-completion of the nerve of this category, would be the stable elements with respect to the fusion system. But what was not clear at that time, whether this category could existed, and if there would be such a category, it could be unique up to homotopy. So they constructed they show a possible candidate for this X in the picture. So then the work that had to be done is to just show that such a category, such as centric linking system associated to an F exists. And the existence and uniqueness of such a centric linking system was answered by first Schermak and then Oliver, using different techniques. Schermak was using the theory of partial groups, and Oliver was using abstraction theory. The abstraction theory that was already established in the work by Brotolevy and Oliver to show the existence of this linking system. So from this point on, so you don't have to talk about the centric linking system, you can just talk about the classifying space of a fusion system. And the classifying space of a fusion system is this space whose cohomology is just the stable elements with respect to F, right? So this is a picture for finite groups. And then what happens with the decompositions. So if BF plays the role of a group, of a non-existing group, we could ask whether this space X, this BF, can also be decomposed using centralizer and subgroup decompositions. And the answer in that case was given by Brotolevy and Oliver in the first paper. But the existence of a normalizer decomposition for saturated fusion system was answered by Asaf Lippmann. And in that case, we don't have an action. If you remember how the normalizer decomposition appeared in the first, in my previous, let me see, yeah, here. So that appears as, I mean, there are a lot of information about G floating around. So it's the action of G on some poset and then using the simplices. And so the way to obtain a normalizer decomposition has to avoid all these G equivariant methods. And what Asaf Lippmann did is use essentially the work of Slominska and show that the centric linking system, the nerve, the mod P, essentially the nerve of the linking system could be described as a homotopy colimit following the spirit of the normalizer decomposition. Usually in essentially all the work of Slominska in EI categories, and then relating everything to the subgroups. So So his result reads like you have a saturated fusion system on a finite P group S, then you have a functor, and the indexing category is the poset of F conjugacy classes of chains of subgroups in a collection. And so this F conjugacy classes, that means that two chains are F conjugate if there is an element of the category F which takes all of one chain into the other chain. So it's just you look at F conjugacy classes. And then the functor, the values of the functor on P, on a chain, is just the automorphisms of this chain, the whole chain, the elements of L, which stabilizes the whole chain, right? In the case of a finite group, then he shows how this relates to the intersection of the normalizers of the elements in the chain. But when we are working in this abstract context, there is no G in the picture. So we don't write it as intersection of normalizers in G. So it's just the elements of the category which stabilizes the whole chain. And then he shows some families for which this is a decomposition. So essentially he deals with F-centric subgroups and elementary abelian subgroups. So the collection of F-centric subgroups, which I think that appear previously, is just this subgroup such that when you take the centralizer in the silo of a P group, which is conjugated to P, it's the center of P. So it's just saying that the centralizer is inside P prime. Right? So, and then now what's a P-local compa group? So a P-local compa group, it's the analog for Lie groups of the fusion systems that I just described for finite groups. That means that the next step that Brotolevy and Oliver took is to see how all this way of describing the conjugacy relations inside a finite group can be taken to the wall of Lie groups. So they describe a notion of a fusion system, but now instead of being based on finite P groups, they are based on discrete p-toral groups. So in that case, your discrete p-toral group is an extension of a discrete p-torus and a finite P group. And the definition of a saturated fusion system on a discrete p-toral group is essentially the same. It's a subcategory of the category of groups where the morphisms contain only monomorphisms. They must contain the conjugations by elements of S. Every morphism, it's the same, but it has some extra actions, has the saturation actions and some continuity actions, because you can have a chain of a finite P groups that this chain of finite P groups, the colimit of the chain is a discrete p-toral group. So, and then what you want is some extension and continuity actions when you have to deal with these situations. And the main examples are given by compact Lie groups. You can describe the fusion system of a compact Lie group in a similar way that we did for finite groups. And then there are new examples that there are the examples of p-compact groups. So the idea of a p-compact group was introduced by Dwyer and Wilkerson. And the idea was to give some homotopy analogs of compact Lie groups at the prime P, but in a different, just from the point of view of finite loop spaces, right? So what's a p-compact group? So a p-compact group is just a finite is X. X is a finite loop space because X is mod P finite. The cohomology of X is finite. The mod P cohomology of X is finite. And the classifying space of Bx is P complete. So it's a mod P finite loop space with P complete classifying space. And There are exotic examples. There are examples of p-compact groups which do not come from compact Lie groups. So the situation is that if you have a compact Lie group, a connected compact Lie group, or just that the group of components is a finite p group, then the completion of G is a p-compact group. But there are also p-compact groups which do not arise in this way. So, for example, examples were constructed by Dwyer and Wilkerson at the prime 2, and Aguade Zabrowski at odd primes, and Notbaum also at odd primes. There are several families of exotic p-compact groups. Exotics in the sense that do not come from compact Lie groups. And here, when I write exotic examples, I mean examples which do not fit in categories 0 and 1. And there are also examples in this context constructed already by Brotolievi and Oliver in their paper, and other examples by Gonzalez, Lozano, and Ruiz also. And these examples of Gonzalez, Lozano, and Ruiz, they built out of taking telescopes of exotic p-local finite groups. So that's another source for constructing exotic examples in this context. Okay, so that's the framework, and then Brotolievi and Oliver, they say that p-local compact group is a triple in which you have a p-discrete toral group. You have a fusion system in this p-discrete toral group, and they also describe a notion of a centric linking system. So this triple SFL is a p-local compact group. So what happens is that Levy and Littman, once the uniqueness, the existence of uniqueness of L was shown for finite groups, they managed to extend to these more general settings of p-local compact groups. So in that case, also in this context, there exists a unique up to equivalence model for L, for the centric linking system. So in the same way as before, we can also talk about the classifying space of a fusion system on a discrete p-toral group, right? So sometimes the terminology is a bit strange because the idea of p-local compact group was to denote the triple, but now that L, we can cross L out of the picture. So essentially, we are dealing with a classifying space of a saturated fusion system on a discrete p-toral group, right? So as I mentioned at the beginning, this project grew up of one of these women in topology. So we were a group from very different backgrounds. So our goal were to just show also the existence of the normalizer decomposition for p-local compact groups. That means for saturated fusion systems on discrete p-toral groups. Then compare this normalizer decomposition with the previous known decompositions for compact Lie groups, and then try to compute new examples. That was our goal. So in that case, so we show that in this context of p-local compact groups, there exist a normalizer decompositions in the spirit of a Schaff-Lippmann's decomposition. So we have a collection of subgroups which contains the F-centric and F-radical subgroups. I already said what's an F-centric subgroup. For F-radical means that when you take the outer automorphisms of an object P, this does not contain any non-normal P subgroup, non-trivial non-normal P subgroup, right? Is similar to the notion of P radical, but in this context of the fusion system. So in that case, there is a functor that goes from the, so again, you can describe the poset of F conjugacy classes of change for p-discrete toral subgroups in this family. And there is a functor which relates to L, and then you have a mod P equivalence under this hypothesis. And again, the automorphisms are described by the automorphisms in L of this subgroup P, of this chain P. Sorry. So these are the elements in L will fix all the chain in in L. Okay. I want to make two remarks, which first that just to show that how to say that it's going to be very useful. the indexing category, first that the indexing category is a poset, it's a finite poset. So, and the other thing is that this we show also in our work that this group, this automorphisms group, is a virtual p-discrete torus. So this is an extension of a discrete p-torus. I mean, it's just ZP infinity, some copies of ZP infinity, and the quotient is a finite group. So it has a normal, it has a normal ZP infinity, a normal p-discrete torus of finite index. So that's for this is kind of a personal observation. I think that the normal, when you are dealing with a finite group and you look at the normalizer decomposition of a finite group, in principle, these intersections of normalizers of chains, this normalizer of chains, they are again finite groups. There are no some specific property. It's like when you're dealing with p subgroups, subgroup decomposition, you can make you can extend properties or construction on p subgroups to G. For the normalizer decomposition, this for a finite group, these intersections of normalized are again finite groups. So in principle, you don't restrict to any special property. But in that case, you are doing it. So because that means that you can describing the classifying space of your fusion system as something you can glue from first a finite poset. So the indexing is a finite poset, so it's better behave sometimes with respect to construction and commuting properties. So it's a finite poset, and the value of the functor is the classifying space of a group. But this group now is just a virtual p-discrete torus. It's a torus extended by a finite group, right? So that means that if you have information and you have properties, or you have something that you can describe out of extensions of discrete p-torus and finite groups, here you have a machinery which allows you to move and construct it for PF, for the classifying space of a p-local compact group, which can be a p-compact group or can be just a compactly group. So if we get back to the Dwyer-Miller decompositions, I just pointed out that all the elements in the diagram, they were two groups or two total groups in that case. So that's one remark, that the way that this decomposition can simplify your point of view on the classifying spaces. Just you have a finite poset and a virtual p-discrete torus and the value of the functor. And the other goal was to understand the relation with the compactly group situation. So if you have a compactly group, the way that you can construct a fusion system just looking at discrete p-toral, right? But discrete p-toral subgroups and p-toral subgroups are related by this construction that you can take the closure of a discrete p-toral subgroup and you will get a p-toral subgroup. And you can take a p-toral subgroup and then work of Feshbach and Dwyer and Wilkerson show you that every p-toral subgroup has a maximal discrete p-toral subgroup inside it. So what they call an approximation or a discretization of the p-toral group. So you can move from this discrete wall to the continuous wall. So every p-toral group has a maximal discrete p-toral subgroups and they are mod p equivalent. But that could happen that you could have a discrete p-toral subgroup inside of a p-toral such that that does not induce a mod p equivalent. So the inclusion, the way that you embed the discrete p-toral subgroup into the p-toral one essentially has to respect the ranked, right? But then when we need to compare these chains of p-toral and p-discrete, so we prove the following, that if you have a maximal p-toral subgroup of G, G is a compact Lie group, S is p-toral. You can take, if you move from discrete to toral, you can take the closure. So if you take chains of F-centric, F-radical subgroups inside G, you take the closures and then you get p-toral, p-centric, p-stubborn, and then you look at, this is the action of G by conjugation. So these are essentially the indexing objects in our categories for the normalizer decomposition. Take the G conjugacy classes. So you have an injection, and which is a bijection if pi naught is a p group. And here you relate the family of F-centric, F-radical, p-discrete toral subgroups to the p-centric, p-stubborn as used by Jakowski and McClure and Oliver for the subgroup decomposition. So you have this inclusion, which is a bijection if pi naught of G is a p group. So you can relate the indexing categories. And what happens with the values of the functor, because as I said before, the values of the functor are these automorphisms in this mysterious category L of these chains, right? Well, in that case, what we show is that in the case of G, this category, this linking system for a Lie group as constructed by Brotto, Levy, and Oliver is built out of the normalizers of these discrete p-toral groups. So it was essential to compare and to show that you can recover something that you can compute out of G, that the normalizers of these discrete p-toral groups just up to mod p equivalents coincide with these normalizers of the closures, right? So we also show that if you have a chain of p-toral groups and you have p-discretizations of this chain, and you look at the stabilizer of the chain, you also have a mod p equivalence on nerves. So everything works fine. So when you look at the automorphisms, when you look at this group which appears here, this odd L of p, when the fusion system is the fusion system associated to a compact Lie group, you can relate this family of F-centric to F-radicals to the family of p-centric p-stubborns, which are, they have been extensively studied in the literature, so there are a lot of information about them. And then you can also relate the values of the functor, this odd L of the chain, with essentially the intersection of the normalizers for G. So when you can put all this information together, when you can reconcile this abstract wall with, in the case of a Lie group, with the previous results, then just what the next goal was to give some examples. Yeah. So using only, we had a first node that we posted in the archive. This first node with kind of warming up. So we compute using only the fusion systems without making any relations to any G homotopy techniques, just only from the fusion systems, and using these decompositions by Slominska, we could just recover the Dwyer-Miller decomposition, push-out decompositions. Yeah, we could get this, the push-outs that I showed you at the very beginning of the talk. And then we can describe new push-out decompositions for UP and SUP at the prime P. The categories are bigger. The categories are bigger, but then just you can relate and you can show that they have also the homotopy type of a push-out. And then the next step is to obtain new description for exotic examples for the p-compact groups that comes from the Aguadé-Zabrowski examples, in which SUP is an important piece. So, so we have a good guess, I would say, just checking details for this. And they could also be described as a motor push-out of p-toral, of virtual p-discrete torus. And then next step will also to deal with exotic examples for fusion systems on discrete p-toral groups. The ones constructed essentially by Lozano, Gonzalez, Lozano, and Ruiz. Yeah. So this is so this was a summary of our project. Okay. So thank you for listening.
Okay. Thank you, Natalia. So any questions for Natalia?
It's good that this talk is online, because otherwise you would get a cold if that was in a room.
So Natalia, do I understand right that you established this mode P homology isomorphisms to verify that if you do the normalizer decomposition for compact Lie group and the corresponding P local compact Lie group, you get the same.
Yeah.
And that's the way you prove that normalizer decomposition works for P. I mean,
for a Lie group, you mean?
P local compact groups. So normalizer decomposition gives you the P completion of the classifying space.
Yeah.
Do you prove this using a Lie group case, or?
No, the idea is that in this result, what you essentially here you don't use anything here. Essentially, just the description of L and the work of Asaf, which inspires how to use Slominska's techniques, right? This could be just settled as it's basically the work of Slominska here. Yeah.
And previous result.
Yeah. But then, yeah, you need to just I have a co-author that says you need to massage the answer that Slominska tells you just to fit into the framework. Yeah. So once you do this massaging, for a Lie group, yeah, it's Brotto, Levy, and Oliver, which show that that if you take the fusion system associated to a compact Lie group, Brotto and Levy and Oliver, they show that this L complete, they construct L explicitly, a model for L, and they tell you that this L completed at P is VG completed at P. So here, the work of Brotto, Levy, and Oliver, what they do is just they give you a model for L, a specific one, and they show that, you know, this is a model for L, and then they use the work of Tchaikovsky, McClure, and Oliver to show that this model for L is VG. I mean, from my point of view, that the hard part is to show that, I mean, this L somehow is like the transporter category I described. I mean, philosophically, it's like the transporter category that I described at the very beginning. All the compositions are encoded inside L, and then you just project to some categories like the Frobenius category, the fusion category, or the orbit category, and then you get different decompositions, but kind of L is the central object, like the transporter category was the central object to relate the subgroup, the normalizer, and the centralizer. And then this, that Brotto, Levy, and Oliver, I mean, this is more just homotopy theory on nerves of categories. But then they show that here you need to show that this is BG completed at P. And for this, you need the previous work of Jankowski, McClure, and Oliver, just to relate. Essentially, they show that in that case, this L completed at P, it can be described as a homotopy limit as a subgroup decomposition, and Jankowski, McClure, and Oliver tells you, oh, but this subgroup decomposition works is VG, right? But for example, for p-compact groups, they also show that for p-compact groups, you have a p-local compact group, as I mentioned in the examples, but they need to work, they need to use homology decompositions for p-compact groups, and one had to show first that homology decompositions, that p-compact groups admit homology decompositions, and that was done in a work where myself and Ranlevy and Dietrich Norton. So.
And this not p-homology isomorphisms you proved for the normalizer of the chains. Mm-hmm. Where do you use them exactly to do? Yeah, these ones, these two theorems.
Yeah.
Use them to not to prove that normalizer decomposition works, but to relate two different decompositions, one for the p-compact groups and one for the p-local. So where do we will use these two theorems in that context?
Oh, you mean? Well, this is for a compact Lie group, right? Uh-huh. So for a compact Lie group, the point is that Asaf Liebman described the normalized decomposition for a compact Lie group in a very geometric way, using geomorphy theory, orbits, actions, and then he gets these descriptions in terms of these intersections of normalizers of GP, very similar to the case for a finite group, right? But when you work again, the problem here again is that if F is Fs of G, yeah, you need to use a specific model for L, right? And Brotto, Levy, and Oliver give you a specific model for L, right? A specific model which is built out of some quotients of these normalizers by some subgroups which are mod p acyclic. It's not directly NGP. It's just NGP and some pullbacks. I mean that the construction is a bit tricky. And I mean, it took me a while to go through all the proofs in the BLO to isolate what I needed. Yeah. So here you really need to use a specific construction of Brotto, Levy, and Oliver of a model for L, right? Once you have this specific model for L, you get this out L of P, right? But this out L of P is just it's not directly the intersection of normalizers, because in the process you have been doing some quotients, and then these quotients affect the chains, right? And then you look at the automorphisms of the chain, but these are in L, so you have to take representatives. I mean, it's not directly seen that this coincides. And then there is also these questions of whether the relation between, if I have p-toral and I have a discrete approximation, and I take the normalizer of both of them, you also need to show that from the homotopy type, they are the same when you do, because they are different. Right? They could be different, and then we needed to go and check that the normalizer from the mod p point of view, that the normalizers of NGP and NGP prime, they do not change. Right? So there were several steps. First to identify this OLP in terms of NGPs, right? But these P's are p-discrete. Right? And the work of Liebman is on p-toral groups, not on p-discrete toral groups. Right? So, and then there was this work of okay, now we have to check that they are not P equivalent. So there are several technical steps that you have to go through. But the point is that we needed a specific construction in Brotolevy and Oliver of this L to just have a sense of what's this group here, and then start relating this group to the normalizers of the closures of the discrete p-toral groups. And then you also need to check that when you take closures, in which families are you moving when you take the closure of discrete. If you start with centric radical and you take the closure, then you, I mean, in that case, you have to show that go to under which conditions you have centric stubborn. I mean, there are all these technical issues that it's not like a straightforward to show that that this abstract decomposition agrees with the Liebman's decomposition for a Lie group. Yeah. I don't know if I explain myself.
Thank you. Thank you. I think I understand.
Okay, so any other questions for Natalia? Sorry, Natalia, did I interrupt you? Were you about to say something? Or?
Can I ask one more if nobody is asking? I have 2-3 more questions, but just a simple one. Do you have a centralizer and subgroup decomposition for p-local compact groups?
Yeah, the subgroup decomposition, yes. And I think also the centralizer, yeah, I think it's in the original paper by
in the BLO,
yeah.
For the p-local compact ones.
Yeah, I think so. Yeah, these are the ones they come more, I mean, the subgroup for sure, because somehow is what builds the theory, the abstraction theory. And I would say that the centralizer is also there, but I mean, they describe the centralizers as mapping spaces under some conditions. No, I'm not that sure about the centralizer one. No, I should check the paper right now. Yeah, so, but, because for the p-local finite group, they use techniques of t-factor. I'm not sure, maybe not, I'm not sure now.
One more question, can I ask? In the finite group case, or the fusion systems on the finite P group S, you have this realization with infinite groups, right? You have an infinite group which has a 0 subgroup S, realizes the fusion system for any saturated fusion system. Oh yeah. Do you have a version of this for systems defined on this discrete p-toruses and because they're constructed.
I'm not aware of having seen this result. I'm not sure, maybe not.
Okay.
Because that was done doing some amalgam of.
Yeah, so,
it was amalgam of normalizers.
Yeah.
And then inside, yeah, I know for finite, but I don't know for. But these normalizers, yeah, can be very big, but yeah, I don't know.
I mean, if your normalizers are approximated by the P compact groups, you could take their amalgams in similar way, maybe, but trees of subgroups or trees of normalizers, and then you could build a group which is infinite, but similar to the compact groups. Then you will have a group that realizes the this poset probably as a
and then every morphism could be thought of as a conjugation by something.
Yeah, there will be a group in the background.
I don't know.
Okay.
Yeah. I haven't seen this result anywhere, so, but doesn't mean that doesn't exist. So.
Okay.
No, I don't know. In the case of finite groups, there is also this work of Sejong Park, I think, that he realizes fusion systems inside symmetric groups, right? As a non-silo, I mean, it's just. And then an open question in this theory, which I've been working with Jose Cantarero and half of his student, which we are trying to make some more progress, is that whether the construction of unitary embeddings for these fusion systems maps into BUN completed at P with some nice properties of the fibers. So yeah, that could replace somehow the symmetric group in this case. Instead of a symmetric group, you have a unitary group. So I don't know if there is a way to embed in a big unitary group, you could fit all this structure, but I don't know. Yeah. Sorry, I was not aware of the audience, so maybe I went too slow through the history, and maybe you would like. You would have liked more details, or sorry. But I mean, you can ask me later or just write to me with questions. That's no problem.
Okay. Well, thank you very much, Natalia, for the great talk. So I'll just terminate the session. Okay.
Yeah. Okay. Yeah, it was.